By this point, you have studied lines and linear equations a few times. I want to introduce you to a new type of equation. Before we begin, though, let's review a little about what we already know with lines. One important thing is that we tend to have three different forms for lines. One of them is called slope-intercept form, probably the most well-known form for a line, y equals mx plus b, where we can see the slope is the coefficient on x, and then b is whatever constant is added at the end there. In this case, my b is 8, which tells me that my y-intercept, the place I'm going to hit on the y-axis, is 0, 8. And then from there, I can plot a slope of negative 5/3, which is a downward slope there. So this form is really good when I already know the equation and I'm trying to draw a graph. The other form that's useful is point slope form. This is when I actually know something about the graph, such as 2 points, and I want to go and write the equation. I don't have the equation yet, but I know some things. And for example, if I knew 2 points, I could calculate the slope and then use that slope as well as one of the points to plug in here, and I would have an equation for that line. The third form that we tend to see pretty often is called standard form. This is when it's written as ax plus by equals c. So I got my x and my y on one side, and I have my constant on the other side. This form is really good for comparing to other kinds of equations, as we will get to later. It is also very good for setting up systems of equations. You can solve systems of equations using elimination by addition, or you can solve them using something called matrices. And in both of those cases, it's really helpful to have them in this standard form first. The two main forms for us, though, have been the slope-intercept form and the point slope form. Some things to notice here is that both of the variables are only to the first power. I don't have an x squared in here or y cubed, anything like that. I also don't have x multiplied by y, which would almost be like, increasing the powers there. They are not inside of anything either. So they're not inside of a square root symbol. I don't have a square root of x anywhere in there. They're not inside a set of parentheses raised to a power besides 1. Now here I do have x with the x minus 6 inside of a parenthesis, but it's really being raised to the first power. So not a square or anything like that. The variables are not inside of an absolute value, and they're definitely not inside of a denominator. I don't have a divided by y or divided by x plus 3 anywhere in these equations. We also know, of course, that the graphs of these form lines. So here's the equation that we had in slope-intercept form, y equals negative 5/3 x plus 8. You see our nice line here. Here's our y-intercept of 8. And then from there, if I were to move 1, 2, 3, 4, 5 down, and then 1, 2, 3 to the right, I get a new point, and that's my slope. We had another equation in point slope form, which was y plus 2 equals negative 5/3 times the quantity x minus 6. Notice that that's really just the same line. And our third equation that was there, 5x plus 3y equals 24, you guessed it, yet again, the same line. So all of these are the same line, but they are in different forms. But what would happen if we were to throw in an x squared? So what if we had a term that had an x squared in it, not a y squared? That's for later in mathematics. But if we have an x squared in there, how does that change things up? Well, these are called quadratic equations. And so let's go look at them on a graph. Let's see what those look like. So our first one is y equals x squared. So coming over here, look at y equals, whoa, look at that. That is definitely not a line anymore. In fact, this shape is called a parabola. And it goes on forever and ever on these ends here, and comes down like this and has this turnaround point right here. So this is our graph of y equals x squared. Our second equation, 3x squared plus 2x plus 4y equals 25. Now look at its graph. Again, we get this sort of U shape, a little bit more pointy than a U, but not like a V that's super, super pointy right there at the turnaround. But I get this shape, but this time notice it's opening downward. This is facing a different direction, the opposite direction. But again, still that U shape there. Our next equation, y equals negative 2x squared plus 6x plus 4. Turning that one on. Again, that U shape. This one is opening downward. And yeah, but still basically up or down in how it's shaped. Our fourth equation here, y minus 4 equals the quantity x plus 3 squared. That almost looks like point slope form in some ways. So looking at that graph, y minus 4 equals x plus 3 quantity squared. You'll notice that that turnaround point here kind of looks like it's at negative 3, 4, which sort of has to do with maybe the numbers that are in there. One of the things we're going to continue to work on is to see how different forms of these quadratic equations can possibly help us understand the graphs. Now looking at this one, you may not think that there's an x squared in there, but as we work later on the algebra, you will be multiplying x plus 3 times x plus 3 if you were to expand this, and there would eventually be an x squared in there. I will warn you, however, that this does not simply become x squared plus 9. That would be very, very incorrect algebra. So stay tuned on how we work through that algebra. So these shapes we're getting are called parabolas, and they continue forever on their ends. We also say that they have a domain of all real numbers. So not only do they continue forever going up, eventually as they go further and further to the side, as they go up and up and up, they're also going further to the left and to the right. So we can use any x we want. That's what domain is. Domain are the inputs, in this case the x values that are acceptable. And these have a domain of all real numbers. So being a little more technical here, a quadratic equation is any equation that can be written in the form of y equals ax squared plus bx plus c. So a, b, and c here are some numbers that we just don't know currently. They're like the m and the b in the slope-intercept form, but we call them a, b, and c typically. And a very important thing here is that a cannot equal 0. So if this were 0, if a was 0, I'd get 0 times x squared, which is 0. So it would drop out the x squared term, and I would just be left with an x term and a constant. That would be a line. So it's not a quadratic equation if you don't actually have that x squared. And that means that the coefficient on x squared, a, can't be 0. Now this is typically called standard form for a quadratic equation. And just like with lines, there are some other forms that are extremely useful. A couple of them that you'll encounter soon are vertex form and factored form. And each of these different forms has their purpose and has a reason that they're very useful. And we'll work up to the other forms as we go forward. So the most basic quadratic equation is y equals x squared. If you look for a second up here at the definition, you might think, well, that's not a quadratic equation. I'm supposed to have an a and a b and an x and a c and stuff. But if I were to rewrite this a little bit, we know that x squared could be written as 1 times x squared. And then I could also say that I had added a 0x and a 0. So now I do in fact have it written as a x squared plus b times x plus c, where a is 1, b is 0, and c is 0. As long as a is not 0, it's fine that b or c potentially are. So this in fact is a quadratic equation. And if I come over here and look at its graph, I see, of course, what I've seen several times now, that I'm getting this parabola. This one is opening upward, has that nice little turnaround point. Well, it turns out that the different parts of a parabola have names, and we talk about these different features that these quadratic equations have in their graphs. One of them, which we already talked about with lines, of course, is the y-intercept. And so on this one, we see that the y-intercept is at 0, 5. And as we start going through things, you might start noticing some connections between things. So notice that kind of like a line, when I just had that plus a number out at the end there, it ended up telling me about the y-intercept. So just sort of keep that in mind. Maybe it's a coincidence. Maybe it's something that we can show algebraically why it's true. Continuing on though, our other important feature here that we really want to look at is that turnaround point. Its actual name is a vertex. That is the vertex of the graph. You will also hear it called a lot of other things. In fact, I might accidentally use some of those. It's called an extremum, or an extreme value. It is called a relative minimum. It might be called a local minimum. There's a lot of different potential names. We're going to try to focus on the word vertex for now. And it appears as if that vertex is at the point 2, 1. Now, just based off of a graph, we can't be absolutely certain about that. It's possible that that was actually at 1.999995, comma 0.993. We're not really absolutely certain. Looking at this equation, it seems likely that it should come out and give us kind of some nice numbers, but we're actually going to need some algebra to prove that that's exactly where that is. So now we're just going to go off of the graphs and kind of see what seems reasonable there. The other thing about this graph is that it is opening upward. So we say that this opens upward. Opens upward. Some people will just say it's an up parabola. That's not real correct. Better to say that it's opening upward. Remember that it really should have arrows here. Technology doesn't put that on there for us. But it does technically have arrows and goes on forever. If we were to start drawing these on our paper, eventually, we would want to make sure that we actually put the arrows when we draw these by hand. One other feature then that this graph has, it's pretty important, is sort of an imaginary line. There's an imaginary line right here over which this graph is symmetric. We say it's an axis of symmetry. And what that means is that it's an imaginary line over which we could flip this graph and it would end up on top of itself. If I were to flip this graph over around that line, it would end up on top of itself. Another way to sort of think of that is this side right here, if this is kind of where I place the mirror, would be reflected and look like it lands right here. This side is reflected and looks like it would land right there. So just kind of cutting that parabola exactly in half and both halves look exactly the same is what we mean by an axis of symmetry. So we have axis of symmetry. Notice that I drew it with a dashed line because it's not actually part of the graph. It's just a line that helps me visualize how the graph is shaped. It is a line though, and a line must be written as an equation. We know that vertical lines are always written as x equals. Regardless of what the y is, the x coordinate is always the same. And in this case, that's going to have to be the same as the x coordinate of the vertex. So the equation of this axis of symmetry is x equals 2. So these are just some of the ideas and features about the graphs of quadratic equations, and we want to practice a little now doing that for ourselves. Perhaps the graph isn't already drawn for us. In order to draw those graphs by hand without any technology, we're going to need to continue with some more algebra, but for now, we'll use some graphing technology to help us look at these shapes a little more. I'm going to use GeoGebra. Desmos would also work, a graphing calculator would work. I'm just more familiar with GeoGebra. So let's look at the equation y equals negative 2x squared minus 12x minus 11. So negative 2x squared minus 12x minus 11. Yep, there we have it. We have a parabola. It is opening downward in this case, and it looks like that vertex is at negative 3, 7. If I come in here under my point tool and click a point on here, come back to my mover cursor, I can move that point around until it looks like it's pretty much at the top. And oh, whoa, and it kind of popped into place right there. I was moving it, and then just sort of all of a sudden it sometimes pops right into place. So it seems like it might be at negative 3, 7. Again, this is not an absolute certainty because we're still just sort of looking at things graphically rather than algebraically. There's a tool on here though, under the point tool. I could have instead done extremum. So if I delete this and instead did extremum and just clicked on this graph, it is going to jump right there to that, that vertex there. Oh, sorry, I just kept clicking. You got to come back over here and make sure you click your point or your mover tool again. I'm going to take that, make it a nice color so it pops out a little better at me. All right. Let me get rid of this one. Get rid of that one again, and let's go try that again. Extremum, and pop right there. I'll grab that one and change it to another color. This nice bright pink, or this bright pink. There we go. All right. So what we see here, and I'll actually go and bring in this picture to our notes. What we're actually seeing here is a parabola that is opening downward, has a vertex at negative 3, 7, and we'll talk about the axis of symmetry. So opens downward. You need to label that you're actually saying what the vertex is. Don't just write a point down and somebody's supposed to be guessing what that point is about. So the vertex is at negative 3, 7. And then we have our axis of symmetry. You can't equal an equation, so I put a colon there. And in this case, again, that axis of symmetry has to go through that vertex. It's a vertical line, so it's written as x equals, and therefore it's x equals negative 3. So I'm not entirely sure about every bit of that. I am kind of trusting in using the graph there, which is actually only doing things sort of numerically for me, not algebraically. So we have to be a little careful that we don't say for certain that this is where it is, but it definitely seems very reasonable. So let's look at another one here. Determine the direction, the vertex axis of symmetry for the graph y equals x squared plus 5x plus 9. X squared plus 5x plus 9. So I get this graph right here. Something I'll notice again in this form, which is that standard form, I got that plus 9, which is also showing up as my y-intercept. And now my vertex is a little bit different. It's not nice integer values. Negative 2.5 and 2.75. So coming over here, let me go and grab this picture, pull it over for ourselves here. Got this graph right here. Manipulating that. And so what we are seeing here is that this opens upward. The vertex seems to be at negative 2.5, comma 2.75, I believe it was. And our axis of symmetry is a vertical line, so it's x equals, and it has the same x coordinate as the vertex. All right. However, I do want to point something out here for mathematics. We really do not like decimals in pure mathematics. They are great for word problems and applications. We, of course, absolutely use them in science since our measurements are metric and based off of base 10s. So we love decimals for that. But in math, as you will see when you go forward, it really works a lot better to use fractions. So I want answers to be written as fractions, and I don't mean mixed numbers. So I'm not going to write this as -2.5. I'm actually going to write it as the improper fraction, -5/2. And then 2 3/4, if I were to write that as a mixed number. Hopefully you know the trick of converting that into an improper fraction. You get 11/4. So this is actually the way that we should be giving our answers, with exact improper fractions, not with decimals. And similarly here, I'm actually going to write that axis of symmetry as x equals -5/2. A couple more here. Try to get through these quickly. I have y equals x plus 1 quantity times x minus 2. X plus 1 times x minus 2. X plus 1 times x minus 2. I have this right here. Move that a little bit. Now I see that my vertex is at +1/2 and -2.25. The fact that I'm getting halves and quarters here again is just somewhat of a coincidence of the fact that I've been writing these to have sort of nice numbers in them. We're going to see in a bit that that's not always true. But so we have 1/2 and -2.25 for our vertex. I will jump and do that first. So our vertex is at 1/2 and -2.25 means -9/4. Again, just a coincidence that both of these had halves and quarters in them for now. This one opens upward, and I have my axis of symmetry. Writing this by hand since I have to write the fractions. I have an axis of symmetry at x equals 1/2. Finally, our last one here, y is equal to 2 times the quantity x minus 2/3 squared plus 4/5. Again, I'm not really seeing that square on x, but if I expanded this, I would. In a similar way, if I were to actually multiply this out fully, I'm going to see that there's an x squared. So both of these are quadratic equations. Let's go take a look at this, minus 2/3 and plus 4/5. So 2 times x minus 2/3 squared plus 4/5. All right, did I get that right? 2 times x minus 2/3 quantity squared plus 4/5. All right, so here we go. It's got it graphed there. All right, now I got a little different thing going on here with my vertex. And the reason I'm bringing this up is to just show how I do expect you to be able to convert decimals into fractions. If you need to get some review on that and we'll help with that, make sure you do that. Because this is a skill you should have at this point. So that 0.66667 is actually supposed to be going on forever and ever. It's just a calculator error that it didn't continue going. But I can look at that and probably reasonably guess that that means the vertex's x coordinate is actually supposed to be exactly 2/3. Again, we're not totally certain, but it seems reasonable. And then the 0.8 means 8/10, but if I reduce that, I get 4/5. So there we go. My vertex appears to be at 2/3, 4/5. Well, that's kind of curious given the numbers that were in the equation up there. And this is foreshadowing some stuff that is coming later as we learn some algebra. This is called vertex form. The trick is, how do you get your equation into vertex form if it's not that way? This parabola opens upward. This quadratic equation is a graph that opens upward. And my axis of symmetry is the equation x equals 2/3. So we've seen these quadratic equations with an x squared in them give us parabolas. They have features such as a vertex, an axis of symmetry, they have a direction, and we specify those, the vertex and the axis of symmetry. We want to make sure we use exact improper fractions. And for now, we're going to be finding out a lot of this information by just looking at graphs and kind of trusting a graphing software package. But moving forward, we want to learn how to manipulate the algebra to actually prove exactly how these graphs are shaping up the way they are.